Hello, today we'll have class on carbocations. Okay. So carbocations is a term, the first positively charged organic species having a format positive charge on the carbon atom bearing only six electrons. So I write down, the term carbocation, the term carbocation is refer to a positively charged you can see this charged organic species having a formal positive charge, which charge on a carbon atom, bearing only six electrons. Okay. The outermost valence they have 6 electrons. They are positively charged, so they are mostly electrophiles. Okay. So there are many carbocations are there. We can have this positive charge alkyl carbocation. We can have alkyl carbocation. This is RR groups, and then we can have another carbocation. This phenyl. This is okay. We can see phenyl carbocation. And then you can have, if there is CH2 here, then you can have CH2 positive charge. Then you can have benzyl carbocation. Then you can have acyl carbocation. R, C, double bond O positive charge. You can see acyl carbocation. Then we can vinyl carbocation, double bond should be then we have C double bond C. So like this. And the hydrogen here, positive charge. So we can say it's vinyl carbocation, and then you can have allylic carbocation. So you can have ACC, CH2 or CH, and CH2 positive charge here. So all are positive charge carbon atom. So this is allyl carbocation. Etc. So many are there. So I'm giving some examples. So I'm repeating again carbocations. The term carbocations is referred to a positively charged organic species having a formal positive charge on the carbon atom bearing only 6 electrons. So like, for example, alkyl carbocation, phenyl carbocation, benzyl carbocation, and acyl carbocation, vinyl carbocation, and allyl carbocation. So many, etc. We can have so many. So carbocation can also be classified as primary, secondary, and tertiary. So we can classify these carbocations as can be classified as primary, secondary, tertiary carbocations as carbocations. Okay, can classify as, you can see. So carbocations can be classified as primary, secondary. So I can give some examples like CH3 methyl carbocation. And we can have secondary CH3, CH positive charge, and tertiary CH3 positive charge. These are all, so we can say tertiary methyl, and then we can have also another methyl groups, CH2, CH3. This is okay. This also, these are examples of different types of carbocations. Okay, we can classify as this is primary, this is also primary, this is secondary, and tertiary. So like this, so I'm giving some examples of carbocations. Carbocations can be primary, secondary, tertiary, like this. Methyl carbocation is also a primary carbocation. Now let's see the generation of carbocations. How carbocations are generated. Actually, carbocations can be generated by two basic mechanisms. So you can say, now let's see generation of carbocations. Okay. So there are general two methods are there. There are two general methods, basic mechanism for generation of carbocations. First one generation of carbocations by heterolytic fissions, by hydrolysis. You can say heterolytic fission or hydrolysis of ethyl species. So first one is hydrolytic fissions of ethyl species or organic compounds. You can generate the carbocations. So here, say for example, say RL. Okay. So by leaving the carbocations, so you can have ion dissociation. You can have so like this. So where L is the leaving group, the electron pairs is taken by L. Leaving group has taken the lone pair electron, so it becomes negative charge, and R becomes positive charge. So R, we have R is the carbocation. Okay. Carbocation, and L is the leaving group. L is the leaving group. So here the leaving group L undergoes bond hydrolytic fission takes place here. That means the negative charge was taken by L. So that is lone pair electrons was taken by L, so it becomes negative charge here. Suppose many examples are here. I'm giving some examples like methyl, chloromethyl, or you can say this you can say CH3 positive charge plus chloride negative charge. Okay, one example, simple examples I'm giving. So this one of the example for heterolytic fissions means heterolytic fissions heterolysis means one of the group atoms has taken the lone pair electrons bearing the two atoms. Okay, the carbon atoms. This here positive charge become to carbon and negative charge become to the leaving group. So this is heterolytic fissions. This type of formation of carbocations of hydrolytic fission can be observed in many organic reactions. Say one in aliphatic, it can be observed. Formation of carbocations can be observed by hydrolytic fission in many reactions. Say in aliphatic, substitution nucleophilic substitution SN1, nucleophilic, unimolecular substitution reaction, unimolecular substitution reaction. Okay. So this type of heterolytic fissions can be observed in SN1 kind of okay, SN1 in aliphatic. So formation of, I'm repeating again, formation of carbocations by heterolytic fissions can be observed can be found in aliphatic, nucleophilic, unimolecular substitution reaction in SN1 reactions. So I'm giving some, I will give here SN1 reaction. So in SN1 reactions, carbocations can be formed by SN1 reactions as an intermediate. Okay. So these are also heterolytic fissions. Let's see some examples I will give. So CH3 here, CH3, the OTS is the leaving group, and CH3 here, CH3. Okay. So this is by SN1. Then this is really slow reactions, rate-determining reactions. So this is lost. This one is fast is lost. Okay, you've got a carbocation. This first step of SN1 is formation of carbocation. Okay. First step of SN1 reaction is formation of carbocation, and the OTS is the tosylate is ion is the leaving group. So first step is formation. Second step is once this is formed, this carbocation is formed, then this will be taken by the once it is very reactive, so it will be very fast. So let's say OS, nucleophile OS. Okay, it's very fast reaction. So once it is formed, this is reactive, so we got a final product. Okay, CH3 C3 butyl alcohol. Okay. So this is the product. So this all together is SMR reactions. So what I want to say is that carbocations can be generated in aliphatic nucleophilic substitution reactions by heteroactive fission. Here also heteroactive fission takes place in the living group as an intermediate carbocations form. And the second step of the SN1 is taken by the nucleophile, you got product. So in the intermediate, in the second part step. So these are another examples. And even this also can be formed in carbocations, can be also formed. Another example is in aromatic nucleophilic substitution reaction also. This also can be observed in the formation of carbocations can be observed in aromatic substitution reactions, substitution reactions also, in like SN1. Okay. So for examples, I'm giving examples. This one. So let's say diazo compounds, diazonium chloride, positive charge, negative charge. Okay, this is the compound reacted, lost this one, and diazonium. This is diazonium salt. This is diazonium salt. Diazonium salt. Then you got a diazonium ion. Aryl diazonium ion. I lost this one. Okay, aryl diazonium ion is formed by taking with this one chloride anion. Okay, chloride anion attacks this one. You got my loss of this one. This loss is this one. And then chloride ion is lost. This one is lost. Then you got the aryl diazonium ion. Okay, this is aryl diazonium ion. Okay. So fast form. Then loss of this nitrogen is lost is like SN1 type. So SN1 is lost. SN1 slow one process is slow. Then we got a phenyl carbocation. Okay. Plus nitrogen. This is phenyl carbocation. So what I want to say that is that carbocation can also form by heteroactive fission in aromatic substitution reaction as an intermediate. Okay. But then it is going to take by another nucleophile. Then you got a final product. The second step of this is fast reactions. So you got a final product of the S7 type reaction. So in the aromatic substitution reaction also can be formed in carbocations can be formed in aromatic substitution reaction also. This is second reaction. And in the another one also in molecular elimination. Carbocations can also generated in molecular elimination reactions, E1 reactions. So as an intermediate, carbocations can also be formed as an intermediate in molecular elimination reaction. In molecular elimination reactions, E1 elimination reactions. So E1 reactions in E1. Okay, E1 reactions. So carbocations can be formed by heteroactive fissions in molecular elimination reactions. So one example I can say some example we can have used this group and chloride. Okay. So like SN1 loss this one, fastest loss. So SN1 type and slow. So fast carbocation is formed. And this faster is like all similar with the nuclear elimination substitution reactions also. And then chloride is formed, heteroactive fission takes place here. Then the second step elimination reactions, second step is CH2 here and hydrogen here. Okay. Then in presence of the base or chloride, okay, this chloride negative charge will attack here, this will attack hydrogen and losses. So we got this elimination reactions, two groups of remove CH3 plus HCl. Okay, this is a final product. Okay, so this is the E1 mechanisms. So this is giving this E1 mechanism here. Lost this HCl form. Okay, so in the E1 mechanism we got the carbocation as an intermediate. So Some examples I'm giving in nuclear reaction also can be formed in aliphatic substitution reactions, in aromatic substitution reactions, in nuclear substitution reactions also can form. And sometimes in nucleophilic reaction, another example is in nucleophilic rearrangement. So in the rearrangement reaction also sometimes these carbocations can be formed. To get the more stable carbocations are formed. So to get the more stable carbocations, rearrangement takes place. So in some rearrangements, carbocations are formed by migration to give a more stable carbocation. Carbocation. Okay. In short, in rearrangement, carbocations can also be generated. So, for example, let's say C3. So let's say this one, another cyclohexyl group. This one. And this is like earlier one, slow reactions. Loss of this one. We got the carbocation first. Carbocation. This is C2Cl there. Another one. C2Cl. Okay. This one can have this cyclohexyl group and this C2 a positive charge here plus this chloride has gone. Okay. So we got this carbocation. This is also carbocation, but this is CH2 group and this is called the primary carbocation. Okay. So due to get the more stable carbocation, this migration takes place. Okay, the migration takes place. So these groups migrated now. So we got these groups migrated, cyclohexyl groups migrated. So now we have another carbocation, CH3, positive charge, CH2, and cyclohexyl groups. Okay, cyclohexyl group. So this is a now tertiary carbocation. So rearrangement takes place by migration of this group to get a more stable carbocation. So this one, finally this one attacked by nucleophile, you can get, so there's a chloride attacks, so you get a CH3, CH2, cyclohexyl group here, then CH3, then this is attacked by chloride attack here, so you got this chloride. Okay, so the final product. So here, just similarly, I just want to show that carbocations can also be generated by migration, by rearrangement to get the more stable carbocation. So these are examples for. Now let's have another second method for generation of carbocations. Now, okay. So another method of formation generation of carbocation is second method is. So these are already we have discussed already the first one, the hydrolytic fission we have discussed already. All these are all about hydrolytic fission. Now let's have the second method. So by addition to second methods, by addition of electrophile or cations, electrophiles. Okay, you can say electrophiles or cations to multiple bonds. Electrophiles to carbon-carbon multiple bonds. Okay, so that I want to say that carbocations can also be generated by addition of cations to carbon-carbon multiple bonds. Okay, this is another second method. Another one is hydrolytic fission. So here, for example, you can say C-double bond. This is a multiple carbon-carbon multiple bonds reacted with this electrophile or the proton. Okay, this is proton addition takes place. So addition takes place like this. So you can have CZ is positive charge here. So we got a carbocation generated. You can say electrophiles. So now you can say any electrophiles. Cations are reacted. So you can have simulation case. You can say CZ E electrophile here, negative positive charge here. So you got a carbocation here. So this is another one for generation of carbocations by addition of cations or electrophiles to the carbon-carbon multiple bonds. So you can find this one in many reactions, in aromatic solution reaction also you can find electrophilic addition reaction also find this thing, okay, fine. But in, say, for example, say like in aromatic nucleophilic reactions, okay, formulation like this, so like you can get this one, so ketan's. So here, I see here, in here, and this become positive charge here. Okay, this is hydrogen here, so it becomes like this. So we form a carbocation of the form. The only examples I'm giving, so by addition of the double bond. Okay, or even triple bonds also can be observed. In triple bonds also you can have acetylene compounds by reacting with HBr and slow. So we can have this R, C the ones, C, this R prime, okay. R prime, the positive charge here. I want to put the hydrogen is added to one of these carbon atom, so you can have ICI here, and then the positive charge here. Then attack this one again by bromide ion, then you can have CR ice, there one C R prime bromide, okay. So like this you can have. So even triple bond compounds also can be, this intake can be added by electrophiles to give the carbocations, then finally nucleophile attack to give the product. Even not only the carbon-carbon multiple bonds, this addition can also take place to this thing, to heteroatom carbon, heteroatom multiple bonds, so many carbonyl compounds or amines compounds. For example, this carbon heteroatom multiple bonds, I can writing again, okay. Carbon, heteroatom, multiple bonds may also add to may also add an electrophile or cation to give a carbocation. So the carbocations can also generated. Carbocation also can be generated by addition to carbon heteroatom multiple bonds. For example, say imine hydrolysis. In imine hydrolysis, we observe the formation of carbocations. So let's say CH3C, this is amine, okay, NH, and this is phenyl groups. Let's say hydrolysis in water, attacks by water. So first, this is in presence of acid, so this will form this will attack here, so you get a carbocation will form C phenyl and H2 with positive charge here, okay. So then by hydrolysis, we got OH here, or can keep carbon will come, O come, then will go this one. Finally, you get a ketone, CH3 phenyl plus NH3. So OH attack will come and then go like this, okay. So how I want to say that carbon nitrogen, or instead of carbon multiple bonds, carbon nitrogen heteroatom multiple bonds can also take place to give the carbocation, so like this. So I'm giving one example here. Similarly, you can have many examples. Another example is the addition to carbon compounds, say like this. Aldehydes, okay, let's say aldehydes. In presence of acid hydrolysis. So first phosphorylation takes place, this one will attack. So you can have COOH, positive charge here, and hydrogen. Then this will go like this. So you got a RCOH, positive charge here, and then hydrogen here, aldehydes. Okay. So this again finally attacked by water. You get oil. This oil will come, then hydrate unstable. This is called hydrate. And OH will attack here, hydrate OH. This is unstable, okay, they undergo further rearrangement. Okay, this, so one example I'm giving you. Ethanol also can be used here instead of water. So these are I'm giving like the examples, okay. So even the So far we have discussed about the generation of carbocations. So generation of carbocations have two main types. First one is hydrolytic fissions of nuclear species, and second type is addition to by addition to carbon multiple bonds or carbon heteroatom multiple bonds. So we have discussed so far. Now let's come to the structure of carbocations. Okay. Structures of carbocations. Carbocations are planar sp2 hybridized. Generally they are trivalent compounds. So you will say structures of carbocations. In general, carbocations are sp2 hybridized with a planar, trigonal, planar. Okay, so you can write down here. Carbocations are generally in general. You can say carbocations in general are sp2 hybridized. sp2 hybridized trigonal planar. Have structures, trigonal planar structures. Okay, they have this trigonal compound. In general, the carbocations are sp hybridized trigonal planar compounds, cations or compounds. So here you can write down here this one. They have this empty 2p orbital here, and they can have this like this. Okay, so let's say hydrogen here, super methyl groups are giving. Okay, they have empty p orbitals. Backhand 2pz, this is backhand 2pz atomic orbitals. Okay, so these are structures. These are planar, and these angles are 120 degrees. Among the carbohydrogen, this one hydrogen 120 degrees. Okay, they are planar compounds. So this is general. In general, I'm repeating again. In general, carbocations are sp2 hybrid of planar. Angle is around 1 degree between the hydrogen and carbons here. Ice bond in the ice. Okay, angle like this. So this is general structure of carbocations. But there are many different deviations to these general structures of carbocations. So many structures like they can be not planar, or angle might be same case. So for example, say in triphenyl carbocation. Okay, here structure this is not planar, but angles are same. So I write the structures of this like carbon. So you can have in this way. Okay, phenyl groups are. There are 3 phenyl groups. So these are bulkier of these groups, so they can have. These are slightly tilted. This is slightly tilted superpositive stars. These are bulky groups. This kind of slightly tilted. Okay, like a propeller of the fan. So they are tilted. So they are not planar. So they are still sp2 but not planar. Okay, so I'm giving one example that all the carbocations may not be planar or sp2 hybridized, but still the angles are 120 degrees. Still the angle is okay, but the compound is not planar. Like propeller types of fan, twisted. These are bulky groups or phenyl groups. Twisted. The angles are the bonds are twisted, slightly twisted. Okay. So the compound is not angle. Like say bridgehead carbocations, they can have. This also now they are not planar. Another example that angle maybe sp2 still sp2 hybridized, but they are not planar. So many examples are here, and angles also sometimes maybe deviation from the angles also may take place. For examples, I am giving examples. In general, they are sp2 hybridized and planar, and angles around 120 degrees, but their deviation takes place for say C2 or C2. Let's say C2. This is carbocation. Okay, another carbocation, saccharopropyl carbocation. Saccharopropyl carbocation is angle is around 60 degrees. So it is not 120 degrees. Still maybe planar, but sp2 hybridized, but angle is there one angle is 60 degree. So this is deviated from the 120 degree. Similarly, another one, cyclobutane also. Here you can say cyclobutane carbocation also angle around one angle is around 90 degree. Okay, so this deviation takes place. Not only all on the might not be 120. So what I am telling that in general carbocations are planar, sp2 hybridized, trigonal planar having two pieces at empty orbital, two empty vacant. There's a vacant, two pieces orbital. Okay, so I'm taking earlier I have taken here. So like this. Okay, so the vacant two pieces empty or vacant two pieces atomic orbital. Okay, so this is the planar angle is around. See, the angle is 120 degree, but the deviation takes place from this angle as well as the planar compound. So I am giving some examples. Now let's come to the stability of carbocations. Okay, stability of carbocations. Now let's come to the stability of carbocations. Carbocations are generally acting as a electrophiles. They can acting as electrophile. They can have depends on the pK value, pK R positive value depends on. Then second one is branching effect. This is generally you can say branching effect is generally you can say hyperconjugation effect, and then we can have third one is the conjugation or double bond conjugation effect due to conjugated with a carbon double bond, okay, or the triple bond. So we have effect stability of carbocations. I'm repeating again. Stability of carbocations can be determined by the pKr positive and by branching effect, conjugation effect. So by this, so what a pKr. First one is that. So let's say some examples. ROS. Okay, if you're going to hydrolyze this, you can have R positive. Let's say OH positive. Okay. OH. You can have positive water plus H positive water. Okay. You can have alcohol. This mixed with some electrophiles or some, let's say some hydrogen atom. Okay. Or you can say water will come. So like this. So you have this carbocation is formed. So your formation of carbocations is depends on the R positive, depends on this formation of this log of R you will go. So you can have equal to K, or you can say log of R positive, this one R divided by ROS and IH plus. So you can have, depending on this higher value of this pKr value, the higher the stability of the carbocation. So due to the pKr value, any reactions when the carbocation is formed, what I want to say is that any reaction when the carbocation is formed, then the pKr positive value of the will be determine the stability of the carbocation. So higher in this case higher the value of pKr, instead of the value of pKr positive, higher the stability of the carbocation. Stability of carbocation. I'm giving you examples. Only one example I'm giving. When alcohol reacts with proton, then we have protocation. So any carbocation forms, then they got a pKr value. If the pKr value is higher, then stability will be higher, like this. So this is one effect. So one is here. Another one is conjugation, hyperconjugation effect, branching effect. So we discuss about it below. Branching effect is more branching. Second one is branching effect, or you can say hyperconjugation effect. Hyperbranching effect. When more branching, say let's say more branch on the carbocation, as compared to CH3 are here, CH3, and one hydrogen, one methyl group is replaced by hydrogen. We have this tertiary, secondary, and then we have replaced by two hydrogen atoms, difference of methyl groups, and then we have the primary. Another one we again have hydrogen, all hydrogen atom, methyl groups, so methyl carbocation. So we have now this is also primary have carbocation. So we have more branching here. There is more branching here. It is more stable. So the stability is like this: tertiary character, then secondary, and primary, and again methyl carbocations. So how you can explain this? More branching means there are CH3, for example, say in here there are three hydrogen atoms here, hydrogen atom here. You can write the resonance structures. So you have by hyperconjugation effect, you can have CH. This is broken down. Okay, now it comes to this one. Comes CH3, H plus. Okay, here. Similarly, you can write this way also. This one raw lost. You can have H plus, CH. So this one is lost like this. So in this way you can write many structures. Okay, CH3, and so on. So all this all come 3, and for this 3 again 6, and for this again 9. So there will be 9 canonical structures. 9 canonical structures will be there. So when I say more branching, we have more canonical structures. So more canonical structures means more stable. So carbocation will be more stable if they have more canonical structures. So here tertiary carbocation will have 9, and secondary carbocation here will have 6, and this one will have 3, and so none only one will have. So that's why more canonical structures will have more stability of the carbocation. So I can write down here more canonical structures of the carbocations will give more canonical structure, canonical or resonance structures will give more stability of the carbocation. Okay, stability of the carbocation. So this is one example I'm giving. So that's why tertiary carbocations are more stable than secondary, and secondary are more stable than primary, and so on. So this is why this is explained by. So now we can have another effect is a conjugation effect. For the stability of carbocation, conjugation effect is there. It is conjugated with a double bond, there is more effect. So we have third one is conjugation effect. So we have conjugation effect. This. So like for example, more conjugation will give more resonance structures. And so one simple example I'm giving here is vinyl CH2, okay, cation, okay, vinylic cation. Another one we can compare CH3, CH2, CH3 is a profile. Okay. When you compare these two, let's say this one CH2 carbocation here. Here you want double bond here, not double bond here. So this is delocalization. So we can have another resonance structure here. So more stabilized. So we have more double bond, more resonance structure means more double bond, more stability comes. Okay. So what I want to say, the like enzymes, CH2. So we give more canonical structure. You can draw from here. You can draw like this. So many, so on. So many canonical structures. So more canonical structure, more resonance structures will give the stability of the compound. So this is about the stability of the carbocation. Now I'm repeating again. For the stability of carbocation, there are three factors: pK value, pKr value, and second one is the hyperconjugation effect or branching effect, and third one is conjugation effect. So these are about the stability of carbocation. So after this we can take next class we will have non-classical carbocation. Okay.